Hello everyone, my name is Afreen Siddiqui and I'll be presenting on behalf of my team at MIT and LabSphere our work on integrating globally dispersed calibration in small satellites mission value. The use of Earth observation data has rapidly increased and it is being applied in a number of applications ranging from agriculture to industrial applications to weather forecasting and tracking wildfires. Many of these are important related to public safety, and it's increasingly important that the accuracy of these data sources and data products is maintained and in fact enhanced. Towards this goal, sensor calibration, which is the process of quantitatively determining an instrument's response to known controlled signal inputs, plays an important role. And calibration is important, particularly for new systems that are emerging where multiple spacecraft, multiple platforms are being used, and it's important to combine these different data streams in consistent and accurate ways. Now, sensor calibration is traditionally done to counter the degradation that occurs for sensors. Sensors in space and in airborne systems degrade in performance during their operations. This degradation may be because of UV exposure, thermal variations, and many other factors that overall lead to change in sensor performance. So as that calibration is frequently performed, it allows to establish the accuracy and consistency of the observed results. And as an example, you can see the change in performance in the OLI instrument on Landsat. In large spacecraft, these sensors are routinely and repeatedly calibrated, which helps maintain consistency. However, for small spacecraft, there are no onboard calibrating systems. In some cases, inner calibration is being used, where small spacecraft are using calibration with larger spacecraft, cross calibration with larger spacecraft. However, this has some inherent limitations. You need consistency of spectral bands, spatial location, consistency of viewing geometry to get it right. And even if the two images taken by two different instruments on the same day within a short period of time, um, all of those conditions are met, there can still be important differences because of changes in the solar illumination angle, changes in the atmosphere, and with the BRDF. So the utility of independent on-ground vicarious calibration systems is important to assess for small spacecraft missions. And here we present a method that helps us evaluate such systems in a systematic way. But first, let me present some previous work on quantifying architecture value, which then lends an approach to quantify the impact of calibration. Now, we quantify architecture value based on a simple proposition that the value delivered by a specific system architecture is directly related to the useful data provided by that system over its life cycle. So we use the total data return as a proxy for value. Using this approach, we define a metric called the effective data acquired, EDA. We compute this for different target regions, K, and for multiple regions that might be of interest, we sum them over for a particular mission over its lifetime. The effective data acquired is basically based on the total data acquired by the mission, QIJ, as well as multiplied with the quality metric. That quality metric relates to the type of sensor being used. And we take the inverse coefficient of variation, take the product with the data quantity to compute the EDA. Here, as you can see, the mu and sigma relate to the mean and standard deviation of the quality measure. Now we take this EDA and use that as a basis for quantifying value. The specifics of how QIJ is computed are found in our paper, which I refer to you, but I'm showing some key equations here on how QIJ is computed based on the number of ground pixels and bits per pixel, and the quality metric, which can be the signal to noise ratio for imaging sensors, um, um, is used in our case for looking at spacecraft with passive imagers. The signal to noise ratio is a useful measure because it includes a number of instrument-specific and orbit-based variables, which allow for understanding the impact of different orbital and instrument-specific decisions that mission planners or designers might be interested in exploring. Now, using this EDA, we can now compute the net architecture value by linking to the concept of net present value, NPV. NPV is a widely used measure for quantifying monetary value of service providing systems in which streams of in which revenue and cost are to be incurred over a period of time into the future. NPV is given by this formulation, and it is essentially a discounted sum of future revenue and cost streams of a project or a system. So in an analogous way, we compute or define the net architecture value, where we take the EDA, which is the effective data acquired, multiplied with omega, which is a monetizing parameter in dollars per bits. And we discount this out using a discount ratio R over N, which is the total number of time periods over the mission life. Now, using this approach or using this formulation, we can now move on to quantifying the impact of calibration by connecting to this valuation, to this formulation for value. And we basically note the fact that the utility of the acquired data is directly related to its accuracy and quality, and in some cases, timeliness. Now, a sensor's data has highest accuracy at the instant of its calibration, after which it declines over time until the sensor is recalibrated and its accuracy is restored. So this temporal decline in accuracy and thus in its value can be represented with an additional discounting factor, which we call R sub epsilon, and we sort of add that in here in the value formulation. So this provides us now with the basis for accounting for the fact that whether data is calibrated or not and how its quality changes over time. Now, if a fully calibrated sensor is used initially, then the value of R sub epsilon will be 0. However, with the passage of time, the data quality will degrade continuously until the sensor undergoes another recalibration event. So the value of R sub epsilon will essentially rise from 0 up to some level, after which it will go back to 0 when the sensor undergoes calibration, and the process will repeat itself. Now, how fast the value of R sub epsilon rises will depend on, the degradation characteristics of the sensor, environmental disturbances, and many other things. We combine them all into a representative parameter, which we call A in this case, and we use a simple formulation for R sub epsilon for our initial model, given as follows here. Note that these T subs I represent instants in time over the mission lifetime when calibration events occur for the sensor. Now, using this approach and using this formulation, we can compute the system value. We implement this in a modeling and simulation framework that we're developing, calibration value integration analysis tool, which allows for quantitatively modeling the value of spacecraft missions and for integrating the value for globally dispersed calibration systems. Okay, so we use this modeling approach to look at two different cases and provide a proof of concept of our proposed methodology. In the first case, we assume a CubeSat constellation of 12 spacecraft with imaging sensors. The parameters of the spacecraft and the sensors are shown here. We assume that the constellation is viewing in continental United States. We use the trait space analysis tool for constellations TAT-C to run orbital simulations. And the results are shown here in the top figure, in which you can see the frequency at which different points of interest, as they were defined in the simulation, are observed by the constellation over the two-month period. Now we assume that the point that had the highest frequency is the calibration site. And for that site, we compute the effective data acquired. Notice that in this particular case, I want to point out that we assumed for simplicity omega value of 1. The regular R, the discount factor, was assumed to be 0, and we did not account for costs. So with all the simplifications, our value formulation is then given by EDA, the effective data acquired, divided by the discounting factor that is only associated with calibration, and we call this EDA adjusted. You can see the results for EDA adjusted over the different points in time for the simulation, and you can compare that for different values of A. The EDA is different, indicating that there's a difference in the effective data acquired depending on its quality as we are adjusting the discount ratio. So for a particular case, when A equals 0, assuming a case in which there's no degradation at all, the effective data acquired is roughly 2,900 terabytes or so, but that declines to roughly, I would say, 2,400 terabytes if A has a value of 0.25%. That's almost an 18% decline. So now this provides us a basis to now quantify and characterize what the impact of data degradation would be at different rates for a given constellation, as well as the impact of calibration and location of calibration sites and so forth. Now, for the second case, we assume a constellation that is observing the entire planet. So it's global observation, and we assume 4 spacecraft with similar characteristics as before and similar sensors. We do a 90-day simulation, and we assume that the calibration sites have to be located below the Arctic Circle. So we identify sites that have high frequency, and we basically pick a site that had the highest frequency. We define that as a calibration site, shown in the black triangle here. This is actually Fairbanks, Alaska. And we assume that our calibration site is located there. And we run 2 cases, the results of which are shown here. We do a case in which we assume that calibration is present, and we compute the effective data acquired using our sub epsilon formulation as shown. And you can see the result for that case in blue. But then we also run another case in which we assume there's no calibration happening and the data is being acquired by a sensor that is simply degrading over time at different rates. So you can, in this case, see that for this particular simulation and this particular assumptions and the cases that we use, we find that there's actually almost a 60% difference between the case where there is calibration and when there is no calibration when A is 0.25%. So again, this becomes a systematic way of quantifying what the impact of different calibration sites, as well as levels of calibration, as well as the extent of data degradation that might be associated with the sensor would imply for overall system and mission value. For more details of this work, as well as further discussion on the limitations and next step, please visit our paper, Integrating Globally Dispersed Calibration in Small Satellites Mission Value, in the online proceedings for the 34th Annual Small Site Conference. Thank you.